Thank you. Good morning, everyone. So this will be my second lecture. So what I will talk about today is a different application of neural network to high energy physics. In particular, graph neural network, and I will say some word on anomaly detection. So deep learnings. I had showed the schematic yesterday of neural network. Here there are more complex neural network where there are many layers, and what's called the deep learning revolution is when, due to various improvements in the algorithms, to various ideas and on the math, etc., people manage to have it work. So I did say yesterday that you had the universal theorem, which allows any network with one layer big enough to do almost anything. Here we have many layers. The reason for that is that we know how to train this layer, training meaning how to optimize the different parameters of the nodes to be able to do what we want to do, while for a single layer, it doesn't work. So that's for these many layers is the ability to train these neural network, even though we know there exists some one layer network doing the same task. And so the neural network have become more and more complex. And famous one is this one, GoogleNet, which are basically, it's a network of network. Nowadays, that's what it is. We have blocks of neurons doing a particular. And this was a network that's trained to identify images taken from internet. So ImageNet is a famous data set which was released where there was, I think there is a million image where people, as I explained yesterday, people were paid to basically say, in this image, I see a car, a dog, a cat. And then algorithms are trained to identify these images. And the basic idea is that the first node identify small details in the image, edges, shapes, and then the deeper you go, the more complex the representation is. And then you have a face node and a cat node. So this was 2014. This was really the beginning of what's called the deep learning revolution, which we are in still now. And they are the three guys who have been acknowledged about this. They got the Turing Prize, the Turing Award, which is the equivalent of the Nobel Prize for computer science, in 2019. So these are Yann Lequin, Geoffrey Hinton, and Yoshua Bengio. Okay, the thing is that this was on images, and the data which we use, our experiments, are rarely images. People do in astronomy, they have images, but we rarely have images. I've shown already this image, which is typically what autonomous car has to understand. But our data is more like that. So this is an event of a Higgs candidate in the Atlas experiment, where there are two muons, two electrons, and which coming from 2Z, and the 2Z are making for a Higgs boson. And this is obviously a representation of the data, but it is not the data itself. We don't use this data for the analysis. Another example. There is something which is not working very well. Ooh. Yes. Maybe the battery, because I carry on like that. It's full, but another example is this one is from LHCb. LHCb is a forward detector in the on the Large Hadron Collider. With these are measurement planes, these are tracking planes, and all the lines are reconstruction of the.
So battery is just we have this. This is the battery indication.
Ah, okay.
Let me just go back.
It works, but it's also there's a delay between the two, which is confusing. And so each line is a charge trap, but of course nobody. Well, the lines are just a reconstruction of the data. It's not the data itself. And the same story for IceCube. At least one person was working with data. So IceCube, as you probably know, these are PMT, which are in the ice shelf in Antarctica. And each PMT is measuring an energy, a time and energy, yes, of photons coming from muons, coming from muon, muon coming from neutrino, from the other side of the Earth, and then undergoing converting into muon, and then the muon emits Cherenkov light. And then one event is like that, and it's time encoded. So the muon comes from the left, and the color encodes the time delay, and the size encodes the energy. And you can, it's not, you can do nice images, but to deal with these images, you cannot do it. You cannot do it. You have really to go to the data itself. There is one exception, which is a NOVA, which is a neutrino detector, which is in the mine, US, which is receives neutrino coming from the Fermilab accelerators at Fermilab, going through the Earth some 100 kilometers, and then the detector is about 3 meters. The 3 meter was 3 meters and 20 meters long, and then the particles are detected in these cells, and the detector is such that what is measured are the projection of what is happening inside the detector. There's a measurement of the projection on one direction and the other direction. It's the detector itself which does the projection. So there is some loss of information, of the full 3D information, but it's already at the detector level. So when analyzing this data, when using this projection, it's all the data which is there. Okay. So what they have done is to so this is now the two projection, X and Y view for 3 types of events: muon charge current, electron. So you see the muon, the long path of the muon, very clear. Electron charge current, where the electron is somewhere, and then a nuclear interaction. And these two clearly are relatively similar. What they did is that they use they have reused the same neural net, Google net, which was showed before, which was trained on cats and dogs on the internet, on the image from the internet, the same one, and then they put 2 copies of it, one looking at the X view, one looking at the Y view, and then there is a small adaptation modules here and there, and then they are combined. And what they see is that with this, they can have an improvement of 40% of the electron efficiency, which is quite significant. And what is quite nice is that they did this, and then they published, I give the reference, they published the paper on this technique, but then they carry on doing the physics measurement using this technique. So it was not something done just as a proof of concept. It was really used for real in the physics measurement. But this they could do because already they had images. Okay, they could really, what you see here, they could really feed the neural network, which is quite often, or most of the case, not what that happens for data which we have. So we have a hammer and nail problem. As you know, the saying that if you have a hammer in the hand, everything looks like a nail. So the nail is the M, and no, sorry, the hammer is the algorithm. The nail is the physics data. And if it does not fit, either you reshape the nail, and this is called the feature engineering, but you will see it's could be quite simple. Either you reshape the hammer, and then you change the neural network architecture. I will show several examples of this. So the first paper on this from Sadowski-Whiteson, it's already in 2014, so it's quite some time ago. So it's a simple cases where they want, as an example, to separate a heavy Higgs actually, to a WWBB compared to the TT bar top production, which is very abundant at the LHC, with the same panels, but then with the different cinematics. And then what they use are the low-level variables, the momentum vector of the jets and the sound coming from this particle, and also high-level variables. In this case, they are invariant masses of pairs of particles. And then they have this plot. So they compare neural network with one layer, which is really like a BDT. A neural network, deep neural network, which at that time was 3 layers. 3 layers is certainly not considered anymore nowadays, but it was considered to be deep. And what they show is that this is with just one layer. So this is the rock curve, but not sure, there is different way of showing the rock curve. This is the background rejection signal efficiency. So the beta is in this corner. Well, yesterday it was in the other corner, but it's really the same thing. And then the AUC, which is the area of this curve, works the same way. That AUC close to 1 means something which is better. And what they show is that so you start with the low-level variable, only the momentum vector. Okay, you get this. If you use only the high-level variable with more physics information, you get the red one. And if you combine the two, you get the blue one, meaning that the neural network is able to extract more information from the momentum. And then they move to deep learning, so 3 layers, and it's not the same story. Here you have the high-level variables only, okay? And then better, you have either the low-level variables or the low-level with high-level variables. So the fact that these curves agree exactly, it means that the neural network is already extracting all the information from the low-level variable. If you give to the neural network the mass of the pair of particles, doesn't improve anything, meaning that the neural network was able to extract all the information from the low-level variable, plus the AUC here, 0.88, is much better than anything which was there before. Okay, and summarize this as okay, the neural network is learning the physics because it is extracting all the information from the high-level variable. Except, so this was very nice, it was published in Nature Communication, except then they look at a different data set, which is auto-analysis at the LHC, which is more difficult. I mentioned this yesterday. And again, same game, low-level variables for momentum, but high-level variables is much more diverse. And these are the high-level variables which was designed by the experts doing the analysis this was for MATLAS, but CMS will be doing the same. And then the story is a bit different with a simple network. You have now it's now the significance. It's not the AUC anymore, but to compare, it's even better than the AUC. But the story is the same. You have the raw variables, human-assisted, meaning the expert variables, and then all variables. So here you can see that the neural network does not learn everything. Sorry. And then for deep neural networks, at least everything is better, but you have the same hierarchy. So in this case, the when you start, for example, with the human-assisted variables, the expert variables, and then you add the raw variables, you still have an improvement. Okay, meaning that the neural network needs to have this human-assisted, because if you only give the raw variables, you have a poor result. Okay, so there is one caveat is that this was done with Delphi simulation. So Delphi simulation is a fast simulation of something which is either Atlas or CMS, but doesn't really matter, which is not very accurate, but it's normally sufficient as a proof of concept. But the main thing is that I've used quite large number of events, 100 million of events. When you work as an Atlas or CMS, if at the end of the day in your analysis after all selection you have 100,000 events, you are happy. Okay, meaning that the number of events there is at least 2 orders of magnitude larger than what we can use in real life. And that's what I write there. In fact, so despite this proof of concept, there are not so many so far published Lash analysis using deep learning. And the progress recently was really to use more and more variables. I say up to 20, but it's more like up to 50. And then combining the low level one and the high level one. And maybe on this is this problem of the number of millions of events. If you do BDT, you can train BDT quite well with 100,000 events, okay? But neural network, to really get the most out of it, you really need a lot of events, and we never have a lot of events. Meaning you still need to build intelligent variables like this one, a transverse mass of lepton missing ET, this one transverse mass of jets, and so on and so forth. So, which is already what we have been doing for decades, to build intelligent variables capturing what we need to know about specific topology. So this is really the summary. There are quite some development recently on physics-aware neural network. So instead of dealing with form momentum like a PT, eta, phi, and then are just numbers, really to inform the neural network that they are dealing with an object which is a 4-vector, which has some property, which can be combined, etc. And there are a number of recent papers on Lorentz invariant neural network, which are quite promising. There's something which people have tried to do, is that, as you know, at the LHC, we have the data, raw data, we build electron, muon, jets, missing ET, tau, photons, of course, and then try to combine these to find signature for specific events. Here, the idea is, okay, we go directly from the jet, the calorimeter flow, which is represented here, directly to classification. So we feed directly a neural network with this, which is so eta, so which is the angle with respect to the beam axis, and phi, and this is one event, and then you try to have the network distinguish between the different without informing the network that there are some jets, there are some objects which are electrons, etc. And typically, this was done with a supersymmetry search with a convolution neural network. So the convolution is the principle is to have a sliding window on the image, finding different details. And at the end, they have this. So this is again a rock curve. The optimum is at the top left, and the blue is a naive cut based, and then there are different. And what can be shown is the So the CNN is not doing as well as what you have when using directly the jets, but is already doing pretty well. And if you use the CNN together with the jet electron muon information, this is a red curve. This is even better, meaning the CNN is able to extract some information which is not in the list of individual particles, probably because jets is not, when we build jets, we lose information on the structure of the jets or on energy flow between the jets. Okay. There was also a attempt to go deeper into analyzing jets. So this is called jet images. Here we have a large jet, which is a boosted object, and one tries to see whether the jet is coming from a W, so you have two quarks, or coming from QCD. And so once you remove the rotation invariance, these are the average images for the W. So you see the two quarks, okay? Then for QCD, you see the heart of the jet, and then you see the first QCD radiation. So you have to distinguish between these. And so this was done with again with a neural net trained on cats and dogs, and convolutional neural net, as explained before. And the results are quite nice. So this time it is 1 over background efficiency. So the curve should be as high as possible and signal efficiency. And then the comparison is 2-1, which is a variable designed by a phenomenologist, which is to basically look, you have a jet, then you run the jet algorithm, and you see at what point you split the jet into two. And this you can characterize by a variable which is called tau-1. And this variable is characteristic to the fact that there is some substructure in the jet. And so this is the reference, and then a different neural network outperforms this. The thing that this was done again on a Delphi simulation on these jet images, where the information on the depth is lost. And you know very well that the calorimeter, you have first electromagnetic energy, and then you have hadronic energy. And then if you put everything together, you lose quite a bit of information. So that's the next step, which is to take into account the fact that we have a complex calorimeter. And for this, the new development, I will come back to that, are the graph neural network. But I have a whole section on graph neural network. So that's for Atlas. So we can have a simple images, but in fact, in practice, this is a zoom on Atlas calorimeter. We have different layers, and the different layers have a different shape for technical reasons. And then you have to analyze this data. And then when you project everything, you lose information. So the same story is that we should do something in order for the neural network to be able to deal with the complex data which we have. Okay, I will now show things which are bad, or not good ideas, because I wanted to be nice on the slides, which are real bad ideas, which are called the super TML and abstract images. So the idea is really very strange. You start from tabular data, so Excel spreadsheet with events and then list of features, and then you generate images with literally the numbers. Okay, and then these images you feed to a convolutional neural network. Same kind, one trained on cats and dogs. And this was applied. So TML is for tabular machine learning. And they took the XML, which is a public data set on Higgs to tau, and they literally generate images with the numbers which correspond to the PT of the lepton, missing ET, and run. There are two attempts. In the second attempt, they try bigger, the more important features. And they run, and then they pretend. They show here the significance. So the first two are the reference significance on this data set, and they pretend to have in the paper, better result, which is just impossible. And turns out that there was Guy Strong, who has done a very nice paper, which I should have referenced. Is in CMS in thesis in Portugal, and now he's in Padova. He has done a very nice paper on using updated neural network on this data set. So he tried to reproduce the result, didn't work. He contacted them, but he didn't have a good answer. And this was published in a computer vision conference, so with no physics expertise whatsoever. But it's clearly wrong. It's wrong because the technique, the fact that you have a numbers and then you put in an image and then you ask the CNN to reconstruct the numbers which you have already is really a bad idea. Plus they were doing something wrong. The number here cannot be true that they have outperforming the reference method. But there are also physicists who are doing things which are not a good idea as well, which is to generate images like that with eta phi, which is meaningful, but then putting objects where the size of the object indicates the energy. So here is a map of in one event where the size of the position is the right position, and the size indicates the energy of the gamma. Same for charged hadrons in the calorimeter, neutral hadrons, and then the one isolated lepton, different shape, missing ET, different shape. And then they run CNN on that, and it does not work too well. At least they do they analyze that, which is not surprising because again, you have the photons, you have the list of energy and PT eta phi of the photons, and then you put it in an image and you ask the CNN to rebuild this information. Okay, it's not what you should do. You should really, your expertise, physics expertise, should be to help the neural network and not to try to confuse it. Okay, so I've spent 5 minutes on something which you should not do, just to make the point clear. Now I move to graph neural network. So what it is? So this is a classical neural network. Dense. This is called a dense neural network. This is a simpler one with input layer, different hidden layer, and output layer. The second evolution for this is the convolution neural network, which I mentioned, where here you have with filters which move around the image. The thing with the convolution neural network is that the neighbor is really in the image, which is a matrix. The neighbors are really the one with I-1, I+1, I+2. You find all the neighbors like that in an image. That's kind of obvious. But now, what can you do to generalize this idea? What is network? Je pense que information. Yeah, I'm not sure what's happening.
Hello.
Thank you. 1, 2. So it's much more flexible in the sense you can define for whatever objects. I will show example of this. Here is the example was done for three body interacting, where you can define the three hypothetical objects and the forces between the three, and then have them evolve. And so this is how it is much more complex to train. The mathematics is more complex, but at the end it does work. For example, I go back to Ice Cube. Here, the notion of neighbors is not well defined because you have the neighbors on the same line, but then it's a 3D. So what they did do is that they use the graph neural network to encode the PMT information, and then they train to separate muon from cosmic rays. And this is shown here is the baseline, which is a simple analysis. The blue is a convolutional neural network, and the green is the graph neural network. So they have some statistics issue, but you see clear improvement in terms of the efficiency. So this is the efficiency with respect to the false positive rate. So the better is on the top left corner, and there is a clear improvement due to this. And this is one of the very first paper, 2018, on using graph neural network, but now they are really everywhere. And because with the same technique, you can represent tracking. I will come back to that. Tracking information in the detector. You can represent calorimeter information. You can represent particles, jet, lepton, met, and etc. So it's much more flexible, more difficult to put in place, but then it really looks like it's the right hammer for our data. Okay, tracking. So it's something I've worked on, which is the TrackML challenge. So the issue is the following. So this is the tracking at the LHC, where on the left you have the points measured in some. It's a detector which is it could be Atlas or CMS, the future detector, the one which is going to be installed at the end of this run period. And the black points are the measurements. And then you have to connect all the black points into tracks, which more or less come from the center. So the number are huge, is 100,000 points to be grouped in 10,000 tracks of 10 points, about 10 layers of silicon for each track. And it's a bit stupid to do this, but if you do the number of combination, it's just much, much larger than the number of atoms in the universe, which is always the case when you have a combinatorial problem. So of course, you cannot do it by brute force. The tricky thing is that the precision of the points. So each point is 50 macrons about precision, while the volume is very large. These are a cylinder, which is 2 meter, well, 2 meter high and 5 meter long, with different layers. So you have big volumes with very precise measurements. And if you translate this into voxels, this will be 10 to the 14 voxel, which is very, very large. And even if you want to work in projections, you will have billions of pixels. So it's very difficult to have a naive algorithm understand this data. The one thing which saves us is that what we want to reconstruct are very specific features. So a trajectory is, as you know very well, it's an arc of Ellis in space with an axis which is parallel to the z-axis, to the z-axis, even though the magnetic field is not solenoidal, perfectly solenoidal, so you have some effect due to this. And it's a challenge because this plot, or something like this plot, was shown yesterday. This is the resources needed to reconstruct LHC data. And I think it has been shifted, as mentioned yesterday as well. It has been shifted a bit. There is a big increase of luminosity, meaning a big increase in the resources needed, and we are not going to have more resources for computing, and so we really need to have ways to reduce the CPU time. So on one side, we are working on improving the software, making it faster. On the other side, we are looking at new ideas. So this was the idea of this challenge, which has run 2018 and 19, and the final paper has just been released last week. And the conclusion is really that machine learning assisted combinatorial tracking. There is no machine learning algorithm which can find track for you. You really have to do it the physicist way to look for this trajectory, but machine learning can assist the traditional algorithm. And one of the examples is track seeding with graph neural network. So one do all possible connection between not all possible, all reasonably possible connection between points, and then run it through the graph neural network, and then you see the efficiency, which is quite good. A different, completely different case for tracking. So this is a prototype for a Dune experiment, which is a liquid argon TPC. So here it's a different case, because in the case of the tracking of the Dashi, we have layers of silicon and the points are on the silicon, of course. While this is a full 3D TPC, and where you have to find the tracks, and the tracks are coming from anywhere, because volume. And so there are specific development for this. It's called URSNet, blah, blah, blah. URSNet for semantic segmentation using submanifold sparse convolutional network. Developed specifically to be able to deal with this. Don't enter the detail, but it works. So it's another example of development specific of the neural network adapted to a specific problem. Okay, I'll do a kind of aparté on machine learning in HEP in the history. So I started to work on the machine learning in 2013, and looking at who has done what, and in the bibliography, I followed the bibliography to find the first papers on using a neural network, and this was the first paper. So there was 3 surprises. First surprise is that the paper was about doing similar things on tracking and calorimetry. So very similar to what I just shown, except of course 30 years later the algorithms are much more sophisticated. First surprise. The second surprise is that, in fact, the guy at that time was working in my laboratory, which has changed name, but it's in our set with the older name of my laboratory. I didn't know about it. And the third surprise is that when I Googled him, he was in fact working in Paris. So I took the RER, the metro, to see him. We discussed it, and he explained me all what he has done. So he's Bruce Denby, and the thing he was working on this is in 1988, and he was the first to do this kind of development. And later, there was a kind of some activity around the neural network, especially led by people in Lund, who have developed a package about a neural network, which was the old style of neural network, which was kind of used at CERN. And just last month, I invited him to my laboratory. So he gave a talk on how he came up with this idea. He really told us that he was doing something boring. And then at the library, he had this paper in the Popular Science magazine about neural network in a new kind of science. And so he started to do these developments. He wrote the paper, and he said that at the end he was almost filed because he had spent time doing funny things on neural network instead of doing what he was supposed to do. And while nowadays, of course, this would everyone is doing this kind of thing. But at this time, this was really something which was not something which was very well seen. And also, he was one of the founder of this conference cycle, which is called ACAT. ACAT is now the conference for AI and physics. And the last one took place in Korea last year. The next one, I don't know where it should be. So it was very interesting to see this. So now he's doing. He has left physics at when the SSC was cancelled in the US. This was mentioned by a speaker 2 days ago, and now he's doing. He has done working on telecommunication. Okay, machine learning for trigger. I just have one slide on this. There is a lot of development on this. This was mentioned by the speaker yesterday. The thing is that the classifiers like BDT or neural network, they are long to train, but once they train, a neural network is very fast to run because it's a simple operation on matrix and vector. So this can be parallelized quite easily. And also, now there are code to put this neural network on FPGA. So I know that you've been working on FPGA in the lab experiments, and there is something which was developed primarily by CMS people. It's called HLS4ML, which helps to input in a FPGA a neural network. And so if you know how to do this, since many different algorithms can be translated into neural network, then it's efficient, it's manpower efficient to do this. And so there are a lot of development these days using this technique of HLS4ML. Another quality of neural network is that computation can be made with low precision. You don't need to do all these matrix multiplication with full 64 bits precision. You can do it with many less bits and still very good result. It's called the compressed model here. It's a neural network using low precision, low number of nodes, and still doing a good work. It's my last set of slides for today. Anomaly detection. So, okay, imagine you in the 16th century, or no, in the 18th century, you arrive in Australia and you see this kind of thing, and you don't believe, you would not believe it is something which exists, because it's a mammal, some kind of mammal with a duck, which lay egg and has duck bill, and so this is related to what a number of people are doing in physics. So anomaly detection, just to explain what it is. So you have some model of, say, standard model, and you want to look for something else. So imagine this is the N like nucleus, this is the regular data, and then you have all like outliers, either alone or a small bunch of things. So there are two ways to detect these outliers. Either you have a model for the outlier and a model for the nucleus, for the model. This is called then supervised. This is really what I've already shown before. semi-supervised, you have a model for the nucleus, and then you don't have a model for outliers. Outliers are defined to be outliers, so not like the bulk of the data. And unsupervised, here you don't have any model, neither for the data, neither for outlier, but just then you see that you're able to cluster the data in big blobs and a few other things. Okay, so there are three approaches of anomaly detection. In a supervised way is something which is very useful because we have to use it all the time. For example, you have in daily life of physicists, you have a Monte Carlo production from last year, the one from this year. You want to make sure they are identical, even though they have been produced with different versions of the code. You have two generators, different version of PTIA, for example, or different version of Geant4, or even you have everything is the same, but produced in different computing center. You want to be sure they are really the same. Same for data. You have the data of yesterday, the data of today. It's supposed to be the same. And how can you verify A and B are identical? So usually, what everyone is doing is that you do histograms and you compare histograms and you see whether histograms match or not. But there is a different way to do it, like a supervised machine learning approach, which is really to train a classifier to separate A from B. Okay, you give it A and B, and you tell the classifier, so BDT, neural network, whatever, please try to find a difference in A and B. Okay, and then at the end you have only one distribution to check, and I've shown this before, which is that a classifier really is compressing the information in n-dimensional space into just one dimension, which is the dimension of the score, without losing information. So there can be some distortion of the two shapes. So then the score will be slightly different. And then when you do the ROC curve, there will be some belly like that. Or there could be a big difference. Typically, you have one piece of detector that does not work, and then there will be no electron in this piece of detector, and then you will see a hole, and it will look like that, and then the ROC curve will look like that. So this kind of technique has been used for data quality monitoring. Not sure which control room it is, in fact. I don't know. But as you know, when taking data, you have to monitor that everything is going on. Everything is going on is correct. And there is this nice PhD, in fact, by Adrian Alan Paul, which is one of the first students doing machine learning as a big part of his PhD, which is using this kind of technique to do monitoring of the CMS muon chamber. And this was using convolutional neural network. And then he has plots like that where there is default. So this is a map of the muon chamber. So this is a channel and the layer. And there are some holes in efficiency, which was seen by standard algorithm and also by the machine learning. But there was some cases where the efficiency, instead of going to 0, it was going to, let's say, 50% for a bunch of channels. And this was not completely black, but less so. And this was not seen by the standard algorithm, and this was detected by machine learning. And this is really running using real data. It is not a kind of quick simulation thing. So, and there are many more applications of anomaly detection. And many people are also thinking about it for new physics, because, you know, at the last sheet was said, we found the Higgs. We have not seen anything else. We're doing precise measurement of the Higgs of the top and so on of the standard model. But also we're looking for new models beyond standard model physics. And there are two ways to do it. One way is to say, okay, I have this signature of SUSY, of of whatever, and then I'm looking for this signature, Z prime, so two jets with a resonance at high mass, etc. And then you look for this signature, but you try also, there's always a signature which you don't think about it. Maybe a theorist will think about it in 10 years. So better to find it right now. So people are looking into these techniques to look for the unexpected. Of course, the big issue is that you should not find glitch in the colorimeter. That's not interesting. So you should really find real physics and not a detector problem. That's a separate thing. And so there is a variety of techniques and recent paper searches both in Atlas and CMS using this kind of technique. And this is the end. No, this is yeah. No, I'm done. I'm done for no, I'm done for now, for today. Thank you.
Oh, thank you. Oh, before the question, sorry, I just had to add one point. And you showed us some papers in the neural network. Actually, there was a paper from L3 in 1991 on B physics.
Yes.
The L3 tracker was smaller, so you are not competitive with the other detectors for the B physics vertex measurement. So the neural network was developed for the BB.
For tracking or for what?
For this, basically the Z to BB branching function measurement, the neural network was used to measure that Z to BB branching function
Okay,
in
interesting.
L3.
Interesting.
And it was developed by one of my senior colleagues here, Tariq Aziz.
Okay, very interesting. Very interesting. You will send me the reference.
Yeah.
I will add this at my historical part.
Okay, thanks. Now, there any question or comment from the student?
So you talked about this physics informed neural networks.
Yes.
So how do we go about it? Means, do we introduce these kind of features inside the layers, hidden layers, or there is some other method by training first for the symmetries and then doing it?
No. So the simpler way is really to build. Is as mentioned. You basically build yourself the high level physics information like invariant masses or angles and something like that, and then you add this as feature, and then you train with that. That's a simple way. But the more complex way is really to introduce this information at the level of the architecture of the neural network itself. Okay, you introduce layers which are able to deal with this Lorentz invariance. So it's a more complex, but it's more promising, I think.
Okay. So how do you train these hidden layers? Means, is there a way you train them by hand or what?
No, no, you do. I think I will show this, in fact, tomorrow, how the training is done. But it's automatically trained by an algorithm which is called ADAMS. It's an optimization algorithm. So it's okay. There could be a full course on the neural network and how to do training and so on and so forth. I cannot do these details.
Thank you, Professor, for your wonderful presentations. Can you go in slide number 19, please?
19?
Yeah. Yeah. In that above plot, I think that is the plot between the right ascension, declination, and with the reconstructed energy, is it? And what criteria have you used for the circular regions plotted on the right ascension and declination graph in data analysis? What physical meaning does the overlap of only a certain fraction of each pair of circles carries?
Okay, I'm not sure I get it. So these are the energy in in bins in eta and phi in the detector, which is in this case like the CMS detector. So it's a cylinder. You split the cylinder, you open, and you have these maps. And then the square is energy deposition, and with the map here, the color map. The red circles are the jets, which are constructed by standard jet algorithm, which is a complete standard in particle physics. So the jets are used as a reference to compare with, while the techniques here do not use the jets, but just use these images, and then try to separate different kind of events based on the images, and which are analyzed by this convolutional neural network. And then try to separate between two kinds of events.
Thank you.
Okay.
In raw data, if we don't know which one is signal, which one is background, how we will train the machine learning?
Yeah. So all this, the training is done on simulation. On simulation, as I mentioned yesterday, you know which is signal, which is background. But you have a good point is that so this technique, you rely a lot on having a good simulation, which has to be well adjusted to real data. So you do a simulator, you adjust on real data, and then you train on the simulation. It's very difficult to train on data because on data it's very difficult to have a pure sample of the signal and pure sample of background.
Thanks, David.
Thank you.
Thank you.
Yes. Even 4 more minutes. Yeah.